So welcome to the quick, no more than 1 hour introduction to the central limit theorem and lower order terms. And so central limit theorem and lower order terms. So I am assuming everybody has some general familiarity with probability. Everybody's comfortable with the basics. We have some random variable x, density, say f or f sub x. We sometimes put in the subscript so that when we have multiple variables under consideration, you can quickly look at it and see what's going on. This means the probability, say x takes on a value between a and b, would just be the integral from a to b of the density. And again, there's something similar if we're doing a discrete rather than a continuous. For simplicity, I want to just assume everything is a continuous random variable. We have the moments. And so we'll say the kth moment is the integral from minus infinity to infinity of x to the k times the density. And then the centered moments would be without the prime, and I'll do a colon equals because these are definitions. It's just the integral from minus infinity to infinity of x minus mu times the density dx, where mu is the first moment. And we sometimes write these as the expected value of x to the k, or the expected value of x minus mu to the k. Just in terms of notation. So everybody comfortable with notation at this level? Excellent. Okay. The hope is if you know the sequence of moments, that implies you know the density. If you want, you could make it an if and only if. But it's really easy to go from knowing the density to knowing the moments. That direction is not interesting. The direction that's interesting is, do the moments uniquely determine? So there's lots of things in life where if you know something, it's uniquely determined. If you know the roots of a polynomial, that uniquely determines the polynomial of finite degree. If it's of infinite degree, not necessarily. We have Taylor series where unfortunately you can know the Taylor series, but that doesn't uniquely determine the function. So danger is functions like, f of x is e to the negative 1 over x squared if x is not 0, 0 if x equals 0. The Taylor series of f is just identically 0, as using L'Hopital's rule, you get all of the derivatives at 0 as 0. But the function is not identically 0. So you can be in this terrible situation where the Taylor series exists, it converges to an infinitely differentiable function, and that infinitely differentiable function only agrees with your original function at 0, which is a triviality. So this is the danger with moments. You can fix things by knowing more than just the integral moments. So it is possible to have two probability distributions that have the same integer moments, they even have the same half integer moments. The big result from complex analysis is if you have two distributions that have the same moments for a sequence of moments that converges to a fixed value. So basically, if no, say, fx, and fy give same moments for a sequence, say, kn, with kn converging to some finite k, then basically they're the same. That's the result we really need from complex analysis. How many of you have seen complex analysis? So think accumulation theorem. That's what's really lurking in the background. You can look at their difference. You now have something that's 0 on a sequence. Very different than real analysis. In real analysis, if I give you the function x, let's do x cubed sine 1 over x. if x is not 0, and 0 if x equals 0. This function is continuous. This function is differentiable once but not twice. And this function is 0 infinitely often as you get closer and closer to the origin, but this function is not identically 0. Real analysis is very different than complex analysis. The politically incorrect way I describe it to my students is real analysis is the democratic subject that will take all functions. Complex analysis is the country club that is begging to be, sued for its restrictive policy as to who is allowed to be a differentiable function. It is a huge deal to be complex differentiable. It means you have to have the same limit no matter what path you take. Well, for a function of a real variable, there's two paths, below, above. Not a huge deal to be differentiable. If people are interested, I know I've shared with at least one of you an example of a function of two variables where the limit is 0 as you approach the origin along any straight line or parabola, but not along cubics. You can do strange stuff like this. Okay, so continuing, what do you think the moment generating function gives you? Moments, right? Every now and then we name something well. Okay, today you should all be wearing your engineering hats. What does that mean? So what does it mean if you're wearing your engineering hat, or even worse, your economics hat? Be willing to play fast and loose with the math. Don't worry about justifying everything. Things can be justified. We're trying to keep this to under an hour. Okay. And that doesn't include the commercial breaks, for advertisement purposes. All right. So let's define the moment generating function of a random variable x as follows. It is going to be the expected value of e to the tx, which is the integral from -infinity to infinity of e to the tx times the density dx. Right. So we will assume that our function has whatever decay properties necessary to make these integrals converge, at least in the neighborhood of the origin. So assume sufficient decay, so converge in, say, some interval minus delta delta, which will contain the origin. Okay? How would you try to evaluate this integral of e to the tx times the density? Any thoughts about what we could do to e to the tx? So sometimes people look at the characteristic function, which is the moment generating function at it, which would then be e to the itx times the density. So this is the characteristic function. One of the huge advantages of the characteristic function over the moment generating function is the characteristic function always exists. It's nice to work with objects that are present. You can do a lot more with them. If I give you, for example, f of x is the Cauchy distribution with the density 1 over pi, 1 over 1 plus x squared, that integral is not going to exist in the neighborhood of the origin. So, if your f of x is Cauchy, 1 over pi, 1 over 1 plus x squared, no delta works. And the problem is it's blowing up. You've got the exponential growth on one side. We need at least exponential decay. So this is not going to work. The characteristic function always exists as the absolute value of e to the itx equals 1, and f of x is non-negative, it's a real value. So because it is non-negative, the integral of the absolute value is the same as the integral of the function. This is always going to be finite. So the characteristic function always exists. The moment generating function does not always exist. We will assume we are working with functions that have sufficient decay. If your random variable x has finite support, if it lives between, say, minus b and b, well, then the integral is over a finite region and everything is fine. If your function has rapid decay, think of a Gaussian, then it doesn't matter what exponential I have over there. The Gaussian is going to decay much, much faster. But we need to figure out, how do we deal with this integral? And again, what I have encouraged you to do is to not worry about any convergence or rigorous issues. It's called the moment generating function. What is the moment generating function supposed to get you? The moments. How do you get the moments? You integrate x to the k times the density. What should we do?
Take the derivative with respect to t.
You could try taking the derivative with respect to t, and that is, and then you could set t equal to 0, and then that would give you various moments, yes. So that's one way to, but to get all of them at once, what could we do? What is a power series? This is the same as the integral from minus infinity to infinity, the sum, n goes from 0 to infinity, of tx to the n over n factorial times the density. Well, this is the same as the integral from minus infinity to infinity, the sum n goes from 0 to infinity. We will have x to the n over n factorial times the density. I'm just rewriting things a little bit. Tn dx. What should we do now? I'm sorry? Yeah, flip the order of the sum and the integral. Are we allowed to do that? Yeah, if you're wearing the engineering hat, you can do that. Then you can stop and think, is this possible? You want to use something like the Fubini-Tonelli theorem. If the double integral, integral sum, whatever, of the absolute value converges, then you can switch the order. And so as long as we have sufficient decay, we're okay. So this is going to be the same as the sum, n goes from 0 to infinity, integral from minus infinity to infinity, and then we'll have x to the n fx dx, and then we'll have t to the n. So what will we get when we integrate that part? What do we get when we integrate that function x to the n times the density? That's just the nth moment. So we would just, and we also have a n factorial. So we'll get the nth moment over n factorial times t to the n. And this is why we call it the moment generating function. When you do this integral, you get a Taylor series, and the coefficients of the Taylor series are the nth moment divided by n factorial. If you take n derivatives, the n is going to come down and give you an n factorial from the t. It's going to cancel the n factorial, and you'll just get. So in particular, if we look at the nth derivative at 0, that's going to just be the nth centered moment. So the moment generating function is really nice. As soon as you have something like the moment generating function, you want to ask, what kind of properties does it have? And before going into the properties it has, let me just, without too much detail, talk about convolutions. Is there anybody here who has not seen the density of a sum of independent random variables? Okay. The way you prove this rigorously is you look at the cumulative distribution function. And so let's say we have x and y are independent random variables with densities, let's say f and g. Then x plus y has density f convolved with g, which is defined as minus infinity to infinity of f of t g of z minus t dt. If you think about it, if you want x plus y to equal z, so say you want little x plus little y equal little z, if x equals t, we need y to equal z minus t. And what's the problem if they're independent? What's the probability that that both happens? That's f of t, g of z minus t. You can do this more rigorously with cumulative distribution functions. The probability that big Z is at most little z is going to be the integral of f of t g of s dt ds. T goes, I'll do it this way, ds dt. T goes from minus infinity to infinity. And if I want the sum to be at most little z, then s is going to go from minus infinity to z minus t. And now what you can do is you first integrate with respect to s, and you would get t goes from minus infinity to infinity, f of t, the antiderivative at z minus t minus the antiderivative at 0 dt. And this might scare you a little bit because in general integration is hard, and we don't know what the integral is in general, but the very next line is the way you get the density from the cumulative distribution function is you take the derivative. So if this is the cumulative distribution function for the big variable z, its density is the derivative. And since we're taking the derivative with respect to z, you pass that through the integral, and then that's where you're going to get your convolution.
Where do you get big G of 0?
Oh, sorry, big G of minus infinity. Thank you. And what is big G of minus infinity? This is just going to be 0. And then this is going to be the cumulative distribution function of the random variable z at z. And now you just take derivative with respect to z. The derivative of the cumulative distribution function is the density. So this is one of the reasons why convolutions are so important. If you have independent random variables, the density of the sum is the convolution. And as soon as you have a process in mathematics, you always want to ask, how does this process behave with respect to other processes? For example, moment generating functions. So this leads to properties of moment generating functions. There are two ways to do this part of the lecture. We can see if I remember things correctly and just state them, or we can do mathematical explorations and then at the end of the day isolate, oh, look what we just proved. Let's do method 2. Okay, let's let y equal ax plus b. And let's calculate what is the what is the moment generating function of y? Well, this is just the expected value of e to the ty, which is the expected value of e to the t ax plus b. This is the expected value of e to the atx, e to the bt. Right? Now, when we do the expected value, this is just going to be, the integral minus infinity to infinity, e to the atx, e to the bt times the density dx. That's a constant. We can just pull that out. And so this is going to just be the integral from minus infinity to infinity, e to the at, and I'm going to put that in parentheses, x times the density times e to the bt. But we know what that integral is. For what value of a is it easy to understand that integral? If a equals 0, then it's just going to be 1. If it's 1, if a equals 1, this is just the moment generating function of x evaluated at t. So this is the moment generating function of x not evaluated at t, but evaluated at at. So you just get back the moment generating function of x at at times e to the bt, or if you want e to the bt on the left, you could do that. So if I take a random variable and I rescale it by multiplying it by a constant and then translating it, the moment generating function transforms in a very nice way. So we'll isolate this as a theorem. The moment generating function of ax plus b of t is e to the bt moment generating function of x at at. Okay, so that's our first result. Let's look at another possibility. Let's say y equals x1 plus x2. It's natural to ask, what's the moment generating function of y? And we'll assume that these are independent. Okay, so this is going to become the expected value of e to the t x1 plus x2, or the expected value of e to the t x1 e to the t x2. If we have independent random variables, what is true about the expected value of a product? It's the product of the expected values. How many of you have seen this before? How many of you have not seen this? If you're ever unsure, what you always do is you just go back to the definition and unwind it. And you write this down as a double integral over the variable x1 and x2, and you realize, oh, there's no interaction between them. So this is then the same as the expected value of e to the t x1, expected value of e to the t x2, which is just the moment generating function of x1, moment generating function of x2. And so we get the following theorem. The moment generating function of a sum is the product of the moment generating functions. That's a nice result. And there really is a corresponding result for those of you who are doing Fourier transforms and the L functions paper. The Fourier transform of a convolution is the product of the Fourier transforms. That's really what's going on here. So sometimes you have to be careful. It's not just physicists who speak differently. Depending on which type of mathematics you do, you speak things slightly differently. You're talking about Fourier transforms, Mellin transforms. A lot of times they're equivalent under a change of variables. And so sometimes, if you're reading a book like Patterson, I think has results on Mellin transforms, but you can easily convert that to Fourier transform results. Okay, we need one more result to prove the central limit theorem. Anybody want to suggest a function to calculate its moment generating function? A density. Given that we're trying to prove the central limit theorem, and some of you know what the central limit theorem is, let's do the Gaussian, right? So what is the moment generating function of a Gaussian? So the first thing is, so we say X is normal with mean mu variance sigma squared if the density is 1 over square root of 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. The notation would suck if mu was not the mean and if sigma squared was not the variance. So you can go through and you can calculate that these are the same. We frequently look at the special case when the mean is 0 and the variance is 1. That's the standard normal. The hard part is proving the normalization constant. And so just really quickly for completeness, if we define I to be the integral from minus infinity to infinity of e to the negative x squared over 2 dx, we want to show that that equals the square root of 2 pi. Well, if I look at I squared, I'll use a different variable for each one, x squared over 2 dx, integral minus infinity to infinity, e to the minus y squared over 2 dy. This is the same as the double integral, minus infinity to infinity, e to the negative x squared plus y squared over 2 dx dy. If you listen very closely, you can hear it is screaming at you to change variables, right? This is why I had to make sure that the ticking stopped. I didn't want that to be distracting, right? What variable should you use? Polar. right? It only depends on the sum of the squares. So we switch to polar. So this is now the integral e to the minus r squared over 2. That's a terrible r. R dr d theta. R goes from 0 to infinity. Theta goes from 0 to 2 pi. The theta integral just gives us 2 pi. And then boy, is life good. When you look at the r integral, we have an e to the minus r squared over 2, which kind of scares you. But the derivative of that is negative r. So all that does is it just flips the order of integration, and you get e to the minus r squared over 2, 0 and infinity. So you just get 2 pi. Therefore, I equals plus or minus the square root of 2 pi. As I is greater than 0, I equals the square root of 2 pi. So this just gives us the normalization constant of the Gaussian. It is the square root of 2 pi. All right, let's calculate its moment generating function now. So let's assume x is a standard normal. Well, what if it wasn't a standard normal? Well, then I go back to the earlier result that if I know the moment generating function of x, I can calculate the moment generating function of ax plus b. I can rescale, I can add, might as well make my life easy and just do this. So now the moment generating function of x is going to be the expected value of e to the tx. All right, so this is going to be the integral minus infinity to infinity e to the tx 1 over square root of 2 pi e to the negative x squared over 2 dx. Okay, well, I can pull out the square root of 2 pi. That's not so bad. I have an integral from minus infinity to infinity. I have an e to the negative x squared minus 2tx. Yes? Okay. Hopefully you've noticed something. What have you noticed in how I've written things? Yeah.
So close to being a perfect square.
It's so close to being a perfect square. And that might be why I have written this with a giant blank. Right? Have you ever done any Mad Libs where you get to put in stuff? So there are two things Peter Jones at Yale taught me that you can do. You can add 0 and you can multiply by 1. And then say, well, the log of 1 is 0. There's really only one thing you can do. So it comes down to thinking, what's the right way to do nothing? How should we add 0 here? So we have x squared minus 2tx. What would you love to add in?
T squared.
T squared. So you can add t squared. And because you're adding in t squared, what do you have to do after adding in t squared? Please leave while wearing that or take that off. So after putting in the t squared, what do we need to do? Subtract t squared. So as long as we do that, that's fine. And now this is going to be 1 over square root of 2 pi integral from minus infinity to infinity e to the negative x minus t squared. And then the other one is going to be e to the, over 2, e to the t squared over 2 dx. I can pull the e to the t squared out, over 2 out. And then, the integral of minus infinity to infinity, let's do u goes from minus infinity to infinity, 1 over square root of 2 pi e to the minus u squared over 2 du, where u is just x minus t. So du is dx, x goes from minus infinity to infinity, implies u goes from minus infinity to infinity. Just a really simple change of variables. We know what that integral is. We just did it a moment ago. It's 1. So we now get, this is just going to be, e to the t squared over 2. And so our theorem is if x is normal with mean 0 variance 1, then the moment generating function of x is just e to the t squared over 2. Okay. All right, we still have on the order of 25 minutes to go. Excellent. So now, central limit theorem. Is this a big, important result? How do you know it's a big important result? Yeah,
You have a hat.
I have a hat, yes. And so this is my hat for the Charlotte airport, but it can be used for other purposes as well. And so, yeah, I love being able to wear this on the day. But why? How can you just look at the title and know that this is important? What gives it away? I'm sorry?
That's the word set.
Yeah, it has the word central. In other subjects, instead of central, what would you say?
Fundamental.
Fundamental, right? That's how you should really think about this. This is like, we have the fundamental theorem of calculus, the fundamental theorem of arithmetic, the fundamental theorem of algebra. For those of you who like it, the fundamental theorem of linear algebra. There is one, yes, okay? This is important, okay? So basically, if x1 through xn are nice, IIDRV, say moment generating functions exist in, say, some interval minus delta delta, then x1 plus xn. So what would you expect the average value of x1 through xn to be? I'm sorry?
Something of the sum.
Yeah, for the sum.
It's the n times the mean.
It should be n times the mean. So instead of studying the sum, let's study the sum minus n times the mean. We're throwing away information we know. We know it's supposed to be on average mu each time. We have n of them. We expect this to be of size n times mu. So it's always, I want to compare apples to apples. If you remember the change of base formula from logarithms, you don't need to know logarithms in multiple bases. Once you know it in one base, you can always convert to another. And then this way, we only have to learn in one base. You only have to construct tables in one base. Well, this is the 21st century. Nobody does tables anymore. But in the old days, people used to compute tables. So we know that the sum is supposed to be of size n times mean. So let's throw that out. The next is we know the size of the fluctuations. So if you have independent random variables, is everybody comfortable with the variance of a sum is the sum of the variances? Okay. If I subtract something, it doesn't change the variance. Imagine the average score in my class is 95 out of 100, and I decide to subtract 50 points from everybody's exam because they were wearing inappropriate clothing. Okay. Have I changed the fluctuations about the mean? No. Have I changed the mean? Hell yes. Right? So subtracting can change the mean, but subtracting is not going to change the variance. What would be the variance of a sum? It's the sum of the variances. So each one of the x's has variance sigma squared. So the variance of the sum is going to be n times sigma squared. You get the standard deviation by taking the square root of the variance. This is why its notation is sigma squared. It's basically yelling at you, please take my square root. I'm not the right scale to study things. So if the variance of the sum is n sigma squared, then the standard deviation of the sum is going to be sigma square root of n. So this is the quantity we should study. And we will call this Zn. Then this is going to converge to being a normal with mean 0 and variance 1. So that's the central limit theorem. Now, I'm going to put some things in red because I like using color and it's fun. I'm going to put the mean and I'm going to put the standard deviation. Those are the only moments of the underlying distributions that are emerging. The higher moments are not coming into this quantity Z. And basically, any random variable that's nice, I can always renormalize it to have 0 mean by subtracting the mean. I can then always rescale it to have standard deviation 1 as long as these quantities are finite. And so I can create this quantity Zn that's going to have mean 0, variance 1. What's miraculous is that this converges to being normal. And the speed depends on higher moments. And that's the main thing we're leading up to today is trying to see how these higher moments play a role. Okay, so here is the high level proof. Compute the moment generating function of Zn of t. Show converges to the moment generating function of the standard normal. And then Wizard of Oz, that means densities converge. You basically, click your heels 3 times, there's no place like home, and just hope that all the abstract nonsense works. And if the moment generating functions converge, the densities must converge. This is the hard step. Why does moment generating function convergence imply densities converge? We're not going to get into that. That's where you need to use some results from complex analysis, that if you have a sequence of moments that agree, okay, there's a limit to what we can do in an hour, okay? But hopefully this will give you some idea. It's not unreasonable that if I have 2 densities, one of them maybe is fixed and one of them is a sequence of densities, and the sequence of densities, their moment generating functions are converging to the moment generating function of this, I would then hope that the densities themselves are converging. That I can't have 2 different densities going to the same moment generating function. It's possible that that could happen, and that's why you use technical terms like nice. Nice,
Oh,
right? Nice is basically whatever you need to justify. So if you assume that the moment generating functions exist in a neighborhood about the origin, that's a very strong assumption. That's not always going to be true. If I give you the Cauchy distribution, you can't even talk about this because the Cauchy distribution doesn't have a finite variance. But I could give you the function 1 over 1 plus x to the 4th, or 1 over 1 plus x to the 6th, and those do have variances. 1 over 1 plus x to the 6th does have a variance. 1 over 1 plus x to the 4th has a variance. And so in situations like that, all the moments don't exist, so the moment generating function doesn't exist, but some moments do. A lot of times, if you really want to impress your friends, you can get down to if like the 3 plus epsilon moment exists and is finite, then the argument can be made rigorous. Okay, we all comfortable so far? Watching the clock, we still have time. So recall, I love saying recall from something that was 1 slide ago, Zn is equal to x1 plus xn minus n mu over sigma square roots of n. And we can write this as, the sum k goes from 1 to n of 1 over sigma root n xk minus, it's going to be mu square root of n over sigma. Okay. Please watch the algebra because we only have 15 minutes left, and I really wanted to get this done in an hour. Okay, so try to make sure I don't make a mistake. The moment generating function of Zn of t is going to be the moment generating function of the sum of 1 over sigma square root of n xk minus mu square root of n over sigma t. And the moment generating function of ax plus b of t was e to the bt moment generating function of x at at. Right? And the moment generating function of x1 plus x2 of t was the moment generating function of x1 times the moment generating function of x2 at t. So what we can do is we can use this to simplify things a little bit. So the moment generating function of Zn is going to just be e to the minus mu square root of n t over sigma, the moment generating function of the sum 1 over sigma square root of n xk of t. I'm just using first the fact that I've got b is negative mu square root of n over sigma. Now I'm going to use the moment generating function of the sum as the product, and each one of them is going to just be a 1 over sigma square root of n. So then this becomes e to the negative mu square root of n t over sigma, product k goes from 1 to n, the moment generating function of 1 over sigma square root of n xk of t. But now we use the fact that the moment generating function of ax is the moment generating function of x at at. I'm just doing things in a few more steps just to try to minimize confusion and typo. Right? So this is then going to be the same as e to the negative mu square root of n t over sigma, the product, k goes from 1 to n, of the moment generating function of t over sigma square root of n of x, where x1 dot 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 xn all have the same distribution. The reason is we know that the random variables all are identically distributed. So the x1, the x2, the x3, it doesn't matter. They're all the same. So I'm going to just denote that by x. So this is now the same as e to the negative mu square root of n t over sigma, the moment generating function of x, evaluated t over sigma square root of n, raised to the nth power. And that is the moment generating function of Zn of t. Okay? Now, as t is a fixed number, okay, I will assume most of you cannot do horrible integrals in your head. But if you look at the moment generating function, is there any value of the input t for the moment generating function where you can quickly calculate what the moment generating function is? I'm sorry? 0, right? What is the moment generating function at 0? It's just, so the moment, so when t equals 0, the moment generating function of x at 0 equals the integral from minus infinity to infinity of e to the 0x times the density. Well, e to the 0x is just 1. So you're just integrating the density over all values. What does that equal? Just 1. So if I was really nice, I would ask you to evaluate the moment generating function at 0. Theorem, Miller is really, no. That's a really hard theorem to prove. Let's prove something weaker. Miller is approximately nice. That's much easier to prove. I'm not asking you to evaluate the moment generating function at 0. I'm asking you to evaluate it at t over sigma square root of n. When n is really large, what is t over sigma square root of n? Approximately 0. So I'm approximately asking you to evaluate this at 0. Okay, that's not so bad. So this is what we want to study now. So we have to study the moment generating function of Zn of t, which is e to the negative mu square root of n t over sigma, and then the moment generating function of x at t over sigma square root of n to the nth power. What should we do? We should be having a Pavlovian response. What should we do? Take a logarithm, right? You are Miller students, right? Whenever you see a product, one of your defaults should be, let me take a logarithm. Okay, so let's take a logarithm. So the log of the moment generating function of Zn of t, I'm going to just do the logs quickly. The log of a product is the sum of the logs. The log of an exponent is just bring down the exponent because the log of e is 1. So is everybody happy that the first term is just going to be negative mu square root of n t over sigma plus n times the log of the moment generating function of t over sigma square root of n? Okay. It would be really nice if I knew what the moment generating function were, because then I could just calculate that, take the logarithm. We don't know what it is, but we can write it. So the moment generating function at, say, I'm going to use the letter U, is the sum. I want to be really careful. Let's say k goes from 0 to infinity, mu k prime over k factorial u to the k. I don't want to use n because we already have n for the problem. So this is just the series expansion of the moment generating function. And what are we going to take u to equal? T over sigma square root of n. And does anybody know what the log of 1 plus u is, the Taylor series expansion? I'm writing this log of 1 plus u.
One minus
Nope.
plus
Nope.
Some, well,
So when u equals 0, what do we get?
Zero.
0. So it's actually u minus u squared over 2 plus u cubed over 3 minus, it alternates. And if you think about it, it should, if u is a small positive number, the log of 1 plus u is going to be greater than 0. So it makes sense it would start off as u. So now, if I look at the moment generating function of t over sigma square root of n, well, the first term is when k equals 0, I just get 1. When k equals 1, I get plus mu, and then I've got u, which is going to be t over sigma square root of n. The next term is going to be plus a mu2 prime over 2. Then I'm going to have t squared. And t squared, I'm sorry, u squared, which is going to become t squared over sigma squared n, plus something of order t cubed over n to the 3/2. So everything from this point onward, it's going to have a t cubed, t to the 4th, t to the 5th, t to the 6th, etc. Because, I'm sorry, going to have a u cubed, u to the 4th, u to the 5th, and so on. If you look at u, t over sigma is fixed. Every time you take a higher power, you get another square root of n. So all of the stuff is going to be at least an n to the 3/2, an n to the 4/2, an n to the 5/2, and n to the 6/2. You can show that the contribution of these are negligible. But the first piece is going to be a mu3 prime over 3 factorial, and then you'll have a t cubed over sigma cubed n to the 3/2. And this is where the lower order terms live. This is where those moments start to emerge. They emerge in these lower order corrections. And then it's worth noting that sigma squared is the expected value of x squared minus the expected value of x squared, which is just the expected value of x minus mu squared. This is a standard probability calculation. If you just expand this out, you can show that this identity is true. So what this is saying is sigma squared is the second uncentered moment minus the square of the mean, or the second centered moment is just sigma squared plus mu squared. And that's just going to be useful for substituting what is mu2 prime. Okay. So when we're looking at what's going on, let's copy. So we have this over here. So if I now take the log of mx t over sigma square root of n, that's going to be the log of 1 plus, and my u is going to be mu over sigma square root of n t plus mu2 prime. We just said that that was sigma squared plus mu squared over 2. Then we'll have a sigma squared n down below t squared plus order t cubed over n to the 3/2. And remember, we wanted n times that logarithm, right? Because that's what we had in our quantity. We had n times the logarithm. Well, if you think about what's going on with n times the logarithm, when we expand this out, we're going to get n times this expression is our u. Then we're going to subtract off u squared over 2. Then we're going to add back u cubed over 3. So the first thing is we have the horrible, mu over sigma square root of n t plus sigma squared plus mu squared over 2 sigma squared n t squared. I'm going to drop the order t cubed over n cubed, because when that hits n, that's going to give me something of size 1 over square root of n. The next piece is we subtract off the square, right? And we divide by 2. But when you look at it, when we square things, when the first piece, the t piece hits itself, that's going to give me something of size 1 over n. When that hits the n outside, that's going to be of size 1 that could contribute. When I look at the first cross term, when the t hits the t squared, that's going to give me a 1 over n to the 3/2. When that hits the n, that's going to only give me something of size 1 over square root of n. So I only really care about the first piece here, the mu squared over sigma squared n t squared plus something of size 1 over square root of n. So the big O just means it's a term of size at most 1 over square root of n. Is everybody comfortable with this? I'm just keeping the main terms. And this is where the arithmetic for us, lives. This is where the moments, mu3 prime, mu4 prime, that's where the shape of the distribution lives. It's coming in those terms and how quickly this tends to 0. Okay, so now the log of the moment joining function of Zn of t, we had negative mu, I think, square root of n t over sigma. And now we add n times that. So the n divided by the square root of n is going to give us a mu square root of n t over sigma. Oh, life is good, right? Because when you look at this, this could fill you with some trepidation, the word of the day, because we're going to have something of size square root of n, which is blowing up, but that perfectly cancels with the exponential factor we had from before. Then we're going to have n times this, so we're going to have a sigma squared plus mu squared over 2 sigma squared t squared. And then we're going to have a minus, the n's are going to cancel, and we'll have a mu squared over 2 sigma squared t squared plus order 1 over square root of n. So the first two terms cancel. We have the denominator is 2 sigma squared, the minus mu squareds cancel. We have sigma squared over 2 sigma squared, that's 1/2. So we have t squared over 2 plus order 1 over square root of n. So exponentiating, we get the moment generating function is e to the t squared over 2, and then something of size 1 over square root of n. And this is where the higher moments live. The shape of the density. Okay, that's the central limit theorem under an hour. Okay, we did it. And so hopefully what you can see is all the calculations work out perfectly. If you only care about the main term, it's not so bad. If you want to find the lower order terms, then you just have to be less crude and not just say, and there's this error term over here. Well, let's open up the error term and let's see what it is. So if we wanted the next error term, hopefully we would just have to look at just keeping one more term, but you gotta be a little bit careful with cross terms and whatnot. If your distribution is symmetric about the origin, then the third moment is going to vanish. So it'd be the fourth moment that is the first one that really shows you anything that's going on. So for proofs like this, you might have heard of like the Moses method of statistics, where when he came down from Mount Sinai, not only did he give us 10 rules for good behavior, but he also gave us some laws for statistics. Thou shalt invoke the central limit theorem without the wrath of God if thou hast at least 30 data points. Right? As for most distributions, that's good enough, and we can just say that the central limit theorem kicks in. We can always construct some strange pathological situations where 30 is not enough for you to get good convergence. But for most nice distributions, 30 would work. All right, any questions? So I hope this just, again, big picture was trying to show you how in a lot of these calculations, the main term is universal. And then you can break the main term by looking at higher properties of the system that you're studying. And that's where frequently the interesting behavior lies. It's this rate of convergence. All right, so I'm going to hit stop.